So in equatorial coordinates, we use the celestial equator as the reference plane rather than the horizon, and we get right ascension and declination in the following way. Right? So we have the observer at O, the point overhead is Z, P is the point where you have the pole star, the Polaris. We take a plane which is perpendicular to OP and meets the celestial sphere. This plane is called the celestial equator. And for any object X, to find its coordinates, we draw a great circle, this time from P, X, and see where it meets the celestial equator. And the angle DOX, that's the angle subtended by this object on the celestial equator, is called the declination. And for the second coordinate, we look at the point called the first point of Aries, right? So essentially this first point of Aries, if you look at the celestial equator and we have the ecliptic, that is the path all the planets move in the same plane around the sun, which is called the ecliptic. Observing from the Earth, we observe that the sun moves in the ecliptic and most of the planets lie in this plane. So in this gray I have denoted the ecliptic, the apparent path of the sun around the Earth, and in green I have the celestial equator. The point where the equator plane and the ecliptic plane intersect is called the first point of Aries. Right? So we measure the angle, this becomes our reference point, and we measure the angle from this POD, which is called the right ascension. So using this right ascension alpha and declination delta, we can give the location of any point of the celestial in a unique way. And these coordinates are universal for all observers on Earth, irrespective of the longitude, latitude, or where they observe from. The reason being that this OP axis is the same for all, and hence the plane, a reference plane, the celestial equator, is the same for all. It is the plane which is perpendicular to a fixed line OP, which is same for all observers on Earth, right? While the OZ, which we were talking for horizontal coordinate system, this varies from observer to observer who's moving on a spherical arc. So if we'll spend a little more time looking at this, observe that the stars would move up this way because of rotation of Earth and would go down, right? Again, the north point is taken as you draw a great circle from Z, P, and the point where it meets the horizon is the north point. The side opposite is the south. And things above the horizon are the things the observer can see. The ones below the horizon are not visible to the observer. And due to rotation of Earth from west to east, you see these objects moving along this curve. They go up and come down. I had mentioned earlier that this great circle, zenith pole star all the way around, this is called the meridian. So when an object reaches the meridian, it reaches the meridian two places, one at point G and the other one at H. When it reaches the meridian at G, it is called upper culmination, and that's the highest point that object would achieve during its motion, while edge, when it comes down, it gives you the lower culmination, right? So any object traveling on this, right? So we'll have great circles, which will show you the motion of objects. This star X would travel upwards, and when it reaches the meridian, that's the highest point it can reach in the sky, and then it starts setting. And as it goes down in the western horizon, it sets. TD, we can measure in terms of these angles TOD, or we can measure in terms of the arc TD, right? And from simple geometry, we know that if you have a circle of radius r, and the length of the arc subtended by angle theta is r theta, and if you take r as 1, then you can have theta um, and the arc length is the same. So we can write in terms of these angles or these arc lengths. So right ascension we can say is TOD or the arc TD as mentioned here. Similarly, dx, the arc length dx gives you the declination or the angle dox, which is the declination. From D to G, the arc DG is called hour angle of this object, the star projected on the horizon, and TD is giving you the right ascension of this object, and DG gives you the hour angle. And right ascension of an object plus hour angle of that object gives you the sidereal time, or it's also called the local sidereal time, LST, right? So basically LST tells you how much time would it take for the first point of Aries to culminate, right? This is what your local sidereal time is, time with respect to the stars. And LST is what is often used in observatories for observations. Here we have the celestial sphere with the right ascension and declination from two perspectives. In the one on the left hand side, I have east looking towards us, right? While in the other one, I have west looking towards us. Anyway, it's a matter of this perception. And we see that the objects will rise, culminate, and they go down, right? So any star, which is X here, it will move up. When it reaches the meridian, it will culminate. That's the highest it goes up. And then it comes down, and as it hits the horizon, it starts setting. And here we are viewing the same thing from the western sky. You see that the objects come down, go down the horizon, and this rise up as the rising is shown on the other side of the sphere. And like I mentioned, the pole star has to be drawn in such a way that PN, or the angle NOP, should give you the latitude of the place. Phi here determines the latitude of the place. So obviously Z to N, zenith to N is 90 degrees and PN is pi. So ZP is 90 minus pi, right? And similarly, from P to the celestial equator, this is 90 degrees. That's how we have got it. And if the declination XD is delta, then XP is 90 minus delta. So we can talk in terms of the declination, or sometimes people talk in terms of zenith distance. In this celestial sphere, what we notice is there could be certain stars which would go down but never hit the horizon. This NWS is a celestial horizon, and you see that these curves are not intersecting the horizon. So all the stars which are above a certain thing will never set, and these are called the circumpolar stars. There's a picture on the right, a time delayed picture of the star trails. If you fix a camera on a tripod and take a long exposure, you will see that you will get these star trails, and you see that these stars around the pole star, all these stars are not setting at all. They are circumpolar stars, while these stars are going down the horizon. So all these stars are always above the horizon. You may not see during the day, but they are always there. So depending on the location of the observer, this point would be lower in the horizon or higher up. And like I mentioned earlier, if you are standing on the North Pole, then this would be right overhead. And when you go to the equator, this point, the Polaris point, will be on the horizon. You'll just see semicircular arcs on that. Here's another view of the celestial sphere. And this is just to make clear how we can see the relationship between the arc PZ is 90 minus phi, arc PX is 90 minus delta, and ZX is the zenith distance, which we denote by small z. And we can do geometry with this and get relations and conversion formulae. And this angle PZ and between ZX is the azimuthal angle here. If we are in the southern hemisphere, then you draw the celestial sphere for the southern hemisphere, where the Polaris is below the horizon, and you have the other pole, other end of the pole star Q, which is above, and we have north, south, and the whole thing is reversed. So it's very easy to draw these spheres, but you get a very good perspective of what are the objects which you can observe from a certain longitude, latitude at different times of the year. Coming to the next coordinate system, we use it's the ecliptic coordinate system, in which we use the ecliptic plane as the reference plane. So ecliptic plane, as I mentioned, is the plane in which the planets are moving around the sun, or from Earth, it is the plane where the sun appears to be moving with the plane, right? And we use this plane as a reference plane, and exactly as we had defined a declination or altitude, we measure the angle from the ecliptic plane, which gives you the ecliptic latitude. And from the first point of Aries, the vernal equinox, we measure the angle. Yeah, so we draw a great circle from the pole of the ecliptic. We draw a perpendicular to the ecliptic, going through the center of the Earth this time, not the observer. And the point K is the pole of the ecliptic. KC is perpendicular to the ecliptic. And we draw, for any object X, we draw a great circle this time from KX and see where it meets the ecliptic. And the angle, this ACX, will give you the latitude. And from vernal equinox, this tau C and A, it will give you the longitude. So using ecliptic longitude and latitude, we can give the positions in terms of the ecliptic plane. This coordinate system is often used when we are looking at solar system objects and we are seeing in terms of our ecliptic plane. It becomes easier to visualize. So I'm summing up the three systems which we have seen in a single slide. We had the horizontal coordinate system, where you have observer, point right on overhead is the zenith. We draw a great circle to the star and meet the horizon. Angle above the horizon gives you the altitude, and the angle measured in the horizontal plane from north to the point where the great circle from zenith star meets the horizon gives you the azimuth. So alt azimuth gives you the location of a star uniquely. In equatorial system, we use the celestial equator as a reference plane. Celestial equator is the plane which is perpendicular to the OP axis, right? Is to the axis of rotation. From O to the pole star, we take an axis and take a plane which bisects it at 90 degrees and extend it to meet the celestial sphere. And that becomes our reference plane. And with respect to that, we get the delta. And in the plane, from the first point of Aries, or the vernal equinox, we measure the angle which gives you the right ascension. And in the ecliptic coordinates, we use the ecliptic plane, the plane in which the planets and the sun are moving as seen from the Earth. And we see how above the plane are the star located, which gives you the long latitude of the one. And again from the same point, the first point of Aries, we measure in the ecliptic plane this time the angle measured, which gives you the lambda, which is the longitude. When we are looking at objects at a larger perspective with respect to the galaxy, we use galactic coordinate systems. So we'll be coming to our Milky Way Galaxy in detail in consequent lectures, but our sun belongs to a system of 200 billion stars or more, which forms the Milky Way. And our sun is some 2/3 distance from the center, and the sun is rotating about the galactic center. And we use a coordinate system using galactic plane as a reference plane. So we have our sun here in the galactic plane. Towards the galactic center, we take 0 longitude. And in the plane of the galaxy, we measure longitude 10, 15, 20, 30, 90. Anti-center of the galaxy is 180 degrees longitude and 270 when it's pointing outwards and back to this. And then we measure the object's position above the galactic plane, which gives the galactic latitude, right? So if you have any object here, any star or a cluster or so, we project it in the galactic plane and measure what is the angle. The point is from the galactic center, which gives you the longitude, and then the angle above the galactic plane gives you the galactic latitude. And the point right above will give you 90 degrees north latitude, and the point directly below will be minus 90 degrees latitude, which is the southern galactic pole. Here's a small animation which gives all the 3 important ones. Here, from vernal equinox, we are measuring rise, ascension, and declination of the same object, the star here, alpha and dec. And then we do the same thing in the ecliptic plane. We are measuring from vernal equinox, which is giving you the longitude and the latitude. And then we measure the same thing in the galactic coordinates. By galactic plane, we are measuring the galactic longitude and the galactic latitude. Okay, so here are some formulae, conversion formulae. I would encourage people who are interested in doing a little bit of simple mathematics to form these spherical triangles and find relations between them. And what we have here are relations which convert from from right ascension, declination to uh, altitude, azimuth. And here, if you have altitude and azimuth, these relations give you the declination and right ascension, right? So they are very simple equations to solve. You just have to construct these grid circles and see the relationships and do it. I will not do it in this course, but it is good that you play around with these equations and see this conversion formula, because many times we'll be getting locations in terms of right ascension declination, but locally if you want to see at what altitude or what azimuth an object is, it is very convenient to convert it to horizontal one and do it. Or you can do it from equatorial system to ecliptic to galactic or whatever. There's another way you can do it. There is this link given here. You can go to this site, and if you click it, it will give you NASA's extragalactic database, and this will give you a calculator where you can choose what system you want it, equatorial or galactic or whichever, and then by click of the buttons you will get your output parameters. You can convert it from uh, equatorial to RA deck, from RA deck to galactic or vice versa and so on. Right. So with this I'll end. Thank you.